Hello everyone and welcome to our talk. I'll be presenting a practical ply-based appearance model of woven fabrics by Zahra Montazeri, Soren Gammelmark, Shuang Zhao, and Henrik Jensen. This is a collaboration from University of California, Irvine and Loxian Inc. Fabrics are essential in our daily life, such as entertainment, online retail, and textile design. So their realistic rendering is important. Traditionally, in computer graphics, fabrics are modeled using 2D sheets. They are very light and fast to render and good for distance views. However, there are some challenges. First, they lack the fine-grained details. Additionally, none of them have taken transparency into account, and they only model a reflection. In addition to surface-based models, recently micro-appearance models are introduced, where the cloth is generated down to the fiber level. They offer very high fidelity and details and great for close-up views. However, they are very heavy in size and usually difficult to edit. Also, they only capture light reflection for matching with photographs, and accurate light transmission has been neglected. Our method enjoys both model complexity and fidelity thanks to its middle ground approach. Additionally, light transmission is accurately modeled for very first time that matches with photograph. In the bottom here, we show a real piece of cloth with satin pattern, lit both from front and back. Please note the anisotropic highlight that appears when the only light source is in the back. This is a summary comparing our model with the previous techniques. Please note the last column shows that our model is the only one that captures accurate transmission. Here is a satin scarf modeled using our method with a rotating light to show light transmission as well as reflection. Unlike most prior models that either lack sub-yarn level of information or rely on explicit fiber structure, our expression mainly works at ply level. So this is the middle ground approach, and it offers a good balance between performance and fidelity. Our method involves two main components, geometric and appearance. Let us elaborate geometric first. A quick background on textile hierarchy. Each yarn consists of few strands called plies, and each ply consists of hundreds of micro-diameter fibers. Our model explicitly depicts individual plies as curves, and then fiber-level details are added using texturing techniques. Let's go over the pipeline of our geometry. First, yarn center lines are generated. We take as input a polygonal mesh with per vertex UV coordinate, which captures the fabric's macro geometry, and a 2D weave pattern that specifies the arrangement of the yarns. Using a simple physical model, we compute a tileable set of yarn center lines, as we show the rendering on the left. Then the plies are constructed as helices mapped from a yarn center line space to fabric space, similar to previous procedural techniques. Then fiber level details are added in a procedural texture-based fashion on the surface of individual plies, using normal, tangents, and fiber shadowing maps. Lastly, flyaways are added. Flyaway fibers are those that fray out from the textile. We use a technique similar to Zhao 2011 by randomly modeling these fibers as separate pieces of geometry, depicted as BSB line curves, using user control parameters. Given the same procedural parameters, our ply-based model can closely match the fiber-based reference on the right that has 240 fibers per yarn. Now let us look into how we modeled the appearance. In practice, modeling more details not necessarily results a better approach. Hence, instead of counting for all explicit fiber hits, our model approximates how light scatters within a bundle of fibers and reason about light transport at the ply level. Thanks to this aggregate formulation, our cloth models can be rendered much more efficiently compared to the previous microappearance models. Also, by decoupling reflection and transmission, our light scattering model offers a flexibility to accurately reproduce both effects. This is a ply cross-section along with all the individual fibers inside. When the incident light hit the ply surface, part of it is reflected back as a specular reflection. This component captures the anisotropic specular reflection, and we show, as we show with the rendering on the left. Then the refracted light that originated at the hit point intersects the ply surface from the interior and exits the ply medium. At exit point, we use another specular component to capture the anisotropic specular transmission, as we see on the left. To approximate light scattering within the bundle of fibers that escape the ply medium from the front side, we use a diffuse light component. We call this a body reflection, and it comprised of two terms. The first term is a lomal-cylindrical term that approximates a single scattering light within the ply medium. And the second one is a Lambertian term that approximates multiple scattering within the ply. We observe that the introduction of this lomal-cylindrical term to our reflection model is important for introducing smoothness that can reproduce the same appearance with the real samples. The same body components is applied at exit point to utilize the sub-ply scattering escape from the ply at the back side of the ply medium. So to summarize, on the right we see each of the four components as shown in previous slides, and on the left we show the full rendering. We implemented our technique in KeyShot 10, and it's publicly available if you're interested. Our system is based on path tracing and support both CPU and GPU, and it allows interactive rendering of high-quality cloth. This is the interface of KeyShot 10. We can interactively change any of the parameters. Here the color is changed for warp and weft. We can also change the weave pattern either from the preset options or manually design any pattern. And then turn on the light, we see the anisotropic highlight appears. All right, let's check out some results generated by our interactive ply level model. Here in the bottom row shows real samples under the microscope. And our model can roughly match the geometry and appearance of these models as shown on the top. The parameters are set at this level, and it can be used for any larger scale models with the same material. Here is a larger scale of the satin pattern shown in the last slide. Our model is able to simulate the anisotropic highlights seen in the photograph at macro scale when lit from the back. To obtain the appearance parameters, we solve an inverse rendering problem to minimize the difference of both front-lit and back-lit rendering with the photograph. In these three columns, we show how the previous fiber-based model can match with the photograph. In the fit front and fit back cases, we consider minimizing the differences only for front-lit and back-lit respectively. And as shown in fit both column, our experiment indicates that the fiber-based model has difficulty matching both reflection and transmission simultaneously, while our model can successfully match both lighting conditions thanks to its decoupled approach handling reflection and transmission. Here we show the same comparison for a fabric with a plain pattern, and we show how our model can capture the anisotropic highlights appear in backlighting. And this is another sample with twill pattern. Please note how the backlit shape changes given different weave pattern. Again, these three columns show the comparison with fiber-based model that fails to find a fit for both front and backlighting simultaneously. Here is a lamp model with satin pattern in two orientations. When the lamp is off, our model shows mainly the reflected lighting, showing the texture that is mapped to the surface color. And when it's on, it shows the anisotropic transmission of the light as well as the change of color. Note the backlit highlight orientation is perpendicular to the flat yarn in satin pattern, as we shown in the previous slides as well. We show a rendered animation where a cloth draped onto the ground. Our technique manages to produce a stable and temporally consistent renderings. As for limitation and future work, first of all, our technique works only for woven fabrics due to the simple weave pattern. But a similar methodology can be employed for knit fabrics and handle more complex structures. We would also like to explore a multi-resolution representation to further compress the geometry for distance views. Lastly, cross-sections are assumed to be circular, while in reality they vary and may have concave shapes. This would be an interesting future work as well. In conclusion, we have presented an appearance model for woven fabrics that takes a surface mesh and a weave pattern as input and represents the clothing using interwoven ply curves with fiber level details. Our results show that our model is able to match measured data for both reflection and transmission with intuitive physics-based parameters. Our ply-based representation is easy to edit, it's compact and stable, as the cloth surface is deformed, making it practical to use for woven fabrics. We are grateful to the anonymous reviewers for their helpful comments. This work was supported in part by NSF grant. We also like to thank Dries and Magnus for providing some of the models of our results. Thank you for your attention. Please check out the project website for the paper and the materials. Thank you.